In order to understand the data presented by climate science, we'll be talking about isotopes. And in order to understand isotopes, we need to go back to atoms and talk about atoms. So all universe, we have everything in the universe is made out of matter. And the smallest unit of matter are atoms. And so if we're all made out of matter, and matter is made out of atoms, we're made out of atoms. So it is a natural question to ask, what are those atoms made out of? So the atoms themselves are made out of these subatomic particles, and there are only three types of subatomic particles. There's protons, and there's neutrons, and there's electrons. That's basically saying, like, we're all the same stuff. We're all these same three subatomic particles, no matter what country, no matter if you're a bird or a box, we're all made out of the same stuff. Protons are positive charge or +1, and they do have mass. These are all considered relative masses. They're very small masses. You can see that in terms of kilograms, it's 10 to the minus 27, 10 to the minus 27, or 10 to the minus 31. That's very, 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 very small mass. So we can't see atoms, and we definitely cannot see or weigh any of these protons, neutrons, or electrons. A neutron, that's neutral, no charge, 0, but it does have mass. And then electrons are negative charge, -1, compared to the +1 of the proton. And electrons are considered no mass. Even though it's really, 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 really small, it's considered no mass compared to the other two. So the atom, what holds the mass of the atom are the protons and neutrons, and those are actually all clumped together in the center of the atom called the nucleus, which is similar to having the center of a cell, a biological cell that's called a nucleus. The center of an atom, it has the protons and neutrons in the nucleus. So the number of protons is very important because it determines the identity of the atom. I'll say that again. How many protons an atom has will basically tell you what type of atom it is, or what the element is. Okay, so that's called the atomic number. This atomic number is equal to the number of protons, and it's always going to be a whole number value. So we talked about this atomic number before when looking at the entire periodic table, that this is an address, that every element has a symbol, and that symbol is always equal to the same number, the same atomic number. So the identity of the atom, along with this element symbol and its atomic number, they're all always linked together. Okay. A decimal value is usually about twice as much as the atomic number, not always, but for most of the elements in the periodic table, and that means that the protons account for about half of the mass of an atom, and the other half of the mass of the atom is the neutrons. Why? Because electrons don't have any mass. There are all three of these particles in varying numbers in every single element, but what accounts for the mass that's you'll see in the atomic mass value, the decimal value, that's going to be the protons and the neutrons. How these subatomic particles are arranged inside of the atom is, first you can picture an atom as a three-dimensional sphere, a ball, and this would be a hydrogen atom, and this would be an example here on the right of a helium atom. Okay, so slightly larger sphere for the helium atom, and the hydrogen atom being the smallest, and then moving on up to the atom number 118 being the largest that we know of. So the hydrogen atom has one proton in the nucleus, and this is the only thing that's in there. There's no neutron. This is an average hydrogen atom. And this one proton has its +1 charge. So because all atoms are neutral and have no overall charge, this one proton is matched with one electron outside of the nucleus. So the architecture inside every atom is that you have a nucleus that contains protons and neutrons. Though this hydrogen doesn't have any neutrons, this helium does have protons and neutrons. So there are protons and neutrons in the nucleus, and that's a very dense center, this nucleus. It's got all the mass of the atom, okay? And so this helium atom has 2 protons, and that would be +2 worth of charge, so therefore there are 2 electrons outside the nucleus that balance out, the -2 balance out the +2 worth of charge. As this is shown, the relative size is that the nucleus is very, 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 very small compared to the space around the nucleus where the electron resides. Now, the electron doesn't fill up all this space because there's only one lonely electron. You can think of this space as like the neighborhood where the electron can be found. So, for instance, if I were on the SMC campus and I put a dime down on the ground in the middle of the science building, I would put a dime there, and that dime would be equivalent to the size of the nucleus. A ton of space around the nucleus, a lot more that's shown here. An isotope is when you have an atom of an element that has a different number of neutrons. Remember, the number of protons is always going to be the same for atoms of one element. But things you can change are the number of neutrons. That'll give you a different mass because neutrons have mass. So increase the number of neutrons, you'll have an atom with more mass, but it'll still be the same atom if the atomic number or the number of protons is the same. You can also change the number of electrons. That won't change the identity of an atom, but it will change the ion charge value, which we looked at last week. So isotopes are when you have a different atom of one element that has to have the same atomic number, but there's going to be a different number of neutrons, and so the mass of that atom will be different, but what will be still the same will be the identity of the atom. They'll be the same element, and that atom will have the same chemical properties and the same physical properties and will function the same in a chemical reaction as any other atom of that element. So when you take the protons and neutrons and you add them together, it's called mass number. So mass number is the mass of an isotope, and that's because the protons and neutrons have mass, because electrons don't. And when you add up the protons and neutrons, you can call that the mass number. So these are showing isotopes of carbon. This is carbon 12, carbon 13, and carbon 14. This number, the 12, the 13, and the 14, those are all the mass number of that individual isotope. So how these are all the same, are they all have the same element symbol, C, or element name. They're all carbons, which means they all have the atomic number 6. Okay, so that's the number of protons is 6. So this isotope also has 6 neutrons. This isotope has 6 protons, but now 7 neutrons to add up to 13. And this isotope of carbon has the original 6 protons, but has 8 neutrons to add up to this mass number of 14. You can add the protons and neutrons to get the mass number, as we did for 12, 13, and 14, or you can take the decimal value from the periodic table and round that decimal value to its closest whole number. So that decimal value is the atomic mass, and it's a calculated value based on the abundance of all the isotopes of an element. But when you're just given a periodic table and you're asked to find the mass number, you will use the decimal value and just round it to the closest whole number. You're not always rounding up. Sometimes if it's less than 5, for that next decimal place over, you're going to just round to the closest whole number in the ones place. Elements can exist as different isotopes. So if you have the same number of protons, that's the same identity. Different isotopes of carbon will undergo the exact same chemical reactions and have the same physical properties. They'll have different numbers of neutrons. That's what these isotopes all show, which means they have different masses. And these are showing isotope notation, which is used to indicate those different mass numbers for the different isotopes. And the isotope of carbon 14, this one, is most important in establishing atmospheric carbon dioxide concentrations from thousands or millions of years ago. There's also an isotope of hydrogen, hydrogen-2, H2, that's important in establishing temperatures from thousands of years ago.
So let's figure out the numbers of protons, electrons, and neutrons for each isotope in this worksheet.